Welcome back. In this video, we will learn how to interpret skeletal structures and convert it into its molecular formula. Let's begin by taking a look at this molecule. This is hexane, and you can see here on the screen, there are actually a variety of different ways to depict the molecule hexane. We have its molecular formula, C6H14, which tells us a very simplified version of the molecule. And from this, we can only really gain its molecular mass. However, using the condensed molecular formula, we can see a little bit more about the structure of hexane. And we can see that we have carbon attached to 3 different hydrogens here on the left. And then that carbon is bound with the other carbons in its backbone. And this shows, again, a general structure for the molecule. And by understanding that carbon makes 4 bonds, we can expand that into its Lewis structure. We also have here some 3-dimensional representations of hexane. You've got space-filling models and the ball and stick model. And this one here on the right shows essentially that the hexane molecule is nonpolar. But what we want to focus on is interpreting hexane in terms of these skeletal structures. So these are actually 4 different ways of many of representing hexane using this skeletal structure. And in this carbon backbone, the skeletal structure, the carbon atoms and the hydrogen atoms are only implied, whereas the non-carbon atoms and hydrogen atoms are shown explicitly. So each carbon atom is represented as being at the end of a line or at the connecting point between 2 lines. So here we have 1, 2, 3, 4, 5, 6 carbon atoms. And then the number of hydrogen atoms is determined based on how many bonds that each carbon needs to make to satisfy its octet. So carbon always makes 4 bonds. And so in the case here with this carbon on the left, only 1 bond is shown. So this we'll call carbon number 2. And so this carbon needs 3 more bonds, and they are all 2 hydrogen atoms. All right, so to summarize here, we've got the notion that each line represents a covalent bond, and that the intersections of those lines or the termini of those lines, the termini and the intersections each represent a carbon atom. Whenever we have hydrogen atoms, those are not explicitly shown, but we'll add them on in order to satisfy the octet of the carbon atoms. All other atoms are explicitly shown. So that includes oxygens, nitrogens, carbons, chlorines, sulfurs, etc. And as well as the hydrogens that are bound to those. We'll sometimes refer to those as heteroatoms. So a heteroatom is any atom that's not carbon or hydrogen. The last thing is that lone pairs are typically not shown, but we would indicate if there was a formal charge. So you can see here in the skeletal structure that the oxygen atom has a bond to hydrogen and a bond to carbon, but the lone pairs are not shown. We know that oxygen needs to have a completed octet. So it has 4 electrons within the bonds, 2 for each bond. Therefore, it needs 2 lone pairs. All right, so let's try this on a skeletal structure here. So from our rules, we know that at each intersection, we have a carbon atom, as well as at the end of any line. Now, we see here, we only have intersections that are relevant. We've got 1, 2, 3, 4, 5. So each of those represents 1 carbon atom. We have 5 nitrogens that are shown, And then in terms of hydrogens, some of them are shown and some of them are not. The hydrogens are explicitly shown when attached to a heteroatom. So we can count a total of 3 hydrogens there. And they are implied when attached to carbon atoms. So for each carbon atom, what we would want to do is evaluate how many bonds are already shown, and then the remaining number of bonds that are needed to fill its octet would be 2 hydrogens. So this carbon here has a bond to a nitrogen, a carbon, and then a double bond to a nitrogen. So it's already made 4 bonds, so it's satisfied. So there's no hydrogens onto this first carbon. Let's go now here to this carbon. We can see here that it has a double bond to nitrogen and a single bond to nitrogen, and that's all. So it does need a 4th bond, and so that means that there should be a hydrogen there. At this carbon, it has a single bond to nitrogen, a double bond to carbon, and a single bond to nitrogen. So it has all 4 of its bonds. It's satisfied. So no hydrogens there. This carbon has a single bond to a carbon, a single bond to a nitrogen, and a double bond to a carbon. So it's satisfied. And then the last one right here, it has a double bond to nitrogen, a double bond, or excuse me, a single bond to nitrogen, and therefore only 3 bonds are shown. We need a 4th bond to hydrogen. So we have 3 explicitly shown hydrogens and 2 implicitly shown. So that means a total of 5. So its molecular formula would be C5H5N5. Thanks for watching. Have a great day.